That's how do you know that the sigma in the old and the new coordinate system would be the same. And when we're talking about this one here and this one here, how do you know that they belong to the same stress tensor? How do you know that they are the same stress tensor? Now, to be able to do that, there is one very specific characteristic that is very important, and it is related to the principal stresses. So no matter, if you remember the example we discussed in the first lecture, no matter what direction you take the coordinate system, if you transform the stress into the principal directions, you are going to get exactly the same principal stresses and principal directions. So this is important. Now, in math, this is the eigenvalue problem. So I'm just going to talk about the eigenvalue problem just briefly today, but we are going to get into the eigenvalue problem in a lot more details later on. Okay, so this is the last section of the lecture. This is related to the eigenvalue problem. So to get the eigenvalue, I'll probably just do it through an example. I think this would be the easiest way to see it. So let us try to find the eigenvalues for this tensor here. It's 10 minus 18. So we have a tensor T, 10 minus 18, and then 6 minus 11. It's just a general mathematical procedure. Mathematicians will just call it the eigenvalue problem. However, it has many applications in engineering. One of them is related to the dynamic of structures and natural mode shapes. And one of them is related to the principal stresses and principal strains. So it is a very important problem, and it has many applications in engineering. So this is why you probably need to solve it. Why it is important to know how to do that. I'm going to explain it again. You have seen it in earthquake engineering. Hopefully this will make it easier for you. But I'm going to explain it again, and I'm going to come back to it in the stress, once we get into the stress, and I'm going to come back to it once we get into the strain. Now, the procedure for solving the eigenvalue problem is relatively simple. You try to make the determinant of the matrix equal to 0. I'm just going to slide it slightly in this direction and then move, okay, and move this one slightly to the right. So to solve the eigenvalue problem, you subtract some value, lambda, from all the diagonal terms, and you make the determinant equal to 0. So the determinant of this is equal to 0. Now the determinant of a 2 by 2 matrix is this one multiplied by this one minus this one multiplied by this one. So it is 10 minus lambda multiplied by minus 11 minus lambda, and then you subtract minus 18 multiplied by 6. All right, this is the determinant of the T tensor. Now, the determinant, I mean, basically when you make the determinant equal to 0, the results will not have any inverse. So the result is going to be singular. And this is going to create one problem that we are going to come back to once we do the eigendirections. Now, first of all, we do the eigenvalues. The eigenvalues are the lambdas that make the determinant equal to 0. For the time being, just think about it as a mathematical problem. Don't worry about the physics of that. It's just the lambdas. We are trying to find the values of lambda that will make the determinant equal to 0. Now, I'm just going to expand that. So you have lambda squared, and then 10 minus lambda, this is minus lambda 10, and then you have minus 11 minus lambda, it's plus 11 lambda, and then you have minus 11 multiplied by 10, it is minus 110. And then you have minus, this is going to be plus 18 multiplied by 6. This is right, 36 multiplied by 8. This is 90, 18. This is 108, right? Did I make any mistakes? Okay, it's correct. So now I want to solve this quadratic equation. I just lambda square minus 10 plus 11, this is plus lambda. And then minus 110 plus 108, this is minus 2. So this is a quadratic equation to solve. The quadratic equation, to solve the quadratic equation, I'll just write the rule for solving a quadratic equation here. Okay. So lambda in this case is going to be two possibilities for lambda. It is b squared minus plus the square root of, sorry, it's not the squared. I'm forgetting how to solve a quadratic equation. It's minus b squared, a and c divided by 2a. So this is a, this is b, and this is c. So a and b both are equal to 1s, and c is equal to minus 2. So lambda 1, 2 is equal to minus 1 plus minus the square root of 1 squared minus 4 multiplied by 1 multiplied by minus 2. This is divided by 2. And then the solution is going to be lambda 1 and 2 is equal to minus 1 plus minus the square root of 1 squared is 1. 4 multiplied by minus 2 is minus 8. Minus 8 by minus is going to be plus 8. So under the square, I have 1 added to 8 divided by 2. So this is basically 1 negative plus minus 1 and 8, 9. The square root of 9 is 3. So it is minus 1 plus minus 3 divided by 2. So this will give me lambda 1 is equal to minus, this is minus 4 divided by 2. It is minus 2. Lambda 2 is going to be minus plus 3. This is 2 divided by 2, and it's going to be 1. So these are the eigenvalues. Yes, thank you. Thank you, Jadid. Yeah, you solved it before I did. Okay, great. And then we need to find the eigenvectors. So the eigenvectors are found by substituting for lambda 1. For lambda 1 equal to minus 2, we have the matrix itself, the original one, 10 minus 18. I'll have minus 2 in there. It's 10 minus 2. I'll probably just make it plus 2. And then you have minus 18. And then 6 minus 11. 6 minus 11 minus 2. So this is basically plus 2. And this is plus 2. Ten plus 2, this is 12. And 11 minus 2, this is 9. Now this is multiplied by n1, n2 should be equal to 0 and 0. Now if you look into these two equations, you'll have two simultaneous equations to solve. So you'll have a 12 n1 minus 18 n2 is equal to 0, and 6 n1 minus 9 n2 is equal to 0. And if you look into that, it's basically the same equation. I just multiply this with 2, you will get this equation. So it's basically the same equation repeated twice. And this is the case because we are using the value of lambda, which makes the determinant equal to 0. The determinant is equal to 0. This would mean that this matrix is basically singular, or there is some rows repeating themselves. Okay, so this is by definition going to happen here. It's going to be the same equation repeated twice. So no surprises in there. So it's basically you have only one equation that you need to solve for two unknowns. One equation and two unknowns. How many solutions I have in this case? It's an infinite number of solutions, because I can simply write this as 12n1 equal to 18n2, or basically I write n1 is equal to 3 divided by 2n2, right? I just divide 18 by 6 and 12 by 6. I get 3 divided by 2. Now, you substitute a value for n2, you get a value for n1. Just choose any value you want for n2, you will get a value for n1, a corresponding value of n1. So these two numbers you get for n1 and n2 would always satisfy this equation. So this equation is correct whenever you choose n1 to be 1.5 n2. Any number is going to satisfy the equation as long as n1 is equal to 1.5 n2. So it is an infinite number of solutions. I'm going to pick, for example, n2 equal to 2. If n2 is equal to 2, this will give me n1 is equal to 3 divided by 2 multiplied by 2. This is equal to 3. And then my eigenvector is going to be 2 and 3. All right, so this is the first eigenvector. The second eigenvector, probably just type it on top of this old one. I have here n and here minus 11. Now for lambda 2, this was lambda 1. For lambda 2 equal to 1, you remember I have two values. So lambda 2 now is the one I'm solving for. So I need to subtract the 1 from all diagonal terms. So it is minus 1, minus 1. 10 minus 1 is going to be 9. And minus 11 minus 1 is going to be 12. Now, again, if you look into this equation, if you multiply by 3 and divide by 2, you'll get this previous equation back. So it's going to be, again, the same equation repeated twice. And you have eventually one equation to solve for. You have 9 minus 18 u2 is equal to 0. So it is 9 n1 is equal to 18 n2. So it is 18 divided by 9 is basically 2. So in this case, if you pick any value for n2, you will get a value for n1. And if you pick 1 for n2, you will have 2 for n1. So I'm going to call this one n1, and then I'm going to call the second one n2. So it is going to be 1 is the other way around. It's 2 and 1. Okay, so the eigenvectors are 2 minus 1. So for lambda equal to minus 2, I have n1, I'm going to call it lambda 1. n1 is equal to 2 and 3. For lambda equal to 1, I have the eigenvalue or the eigenvector n2 equal to 2 and 1. So this is the eigenvalues and the eigenvectors. Now you transform and go ahead. I mean, if you want to try that, go ahead and try it. You transform this matrix. You transform this matrix using a Q matrix into another coordinate system, and you find the eigenvalues and the eigenvectors. You will find always the same eigenvalues and the eigenvectors because this is the same stress tensor. Okay, and as I said, I mean, you're free to build your transformation matrix as an exercise if you want to try it. Build your transformation matrix, apply the transformation, see the transformed matrix, see if you can get exactly the same eigenvalues and eigenvectors. You should be getting exactly the same eigenvalues and eigenvectors. All right, so this is just a reminder about the eigenvalue problem. I'm sure you have seen it in the past, at least, I mean, for the earthquake engineering, you have seen it in there, but you could have seen it also some other places. Now, just one last point. So I said you can have an infinite possibilities for n1 and n2. Usually to agree on some sort of a vector, usually you'll have the length of the eigenvector to be equal to 1. And to make the length equal to 1, you just normalize the vector. You normalize the vector by dividing by the length. So the length of n1 is the square root of the sum of the squares. It is 2 squared plus 9 squared. So it is 2 squared plus 3 squared. So this is square root of 4 plus 9. And then this is going to be 13, the square root of 13. And if you look so you divide n1 by its length, you get it normalized. So n1 normalized is going to be 2 divided by 13, square root of 13, and 3 divided by the square root of 13. And you do the same thing for n2. In the case of n2, you have the square root of 2 squared plus 1 squared. So this is the square root of 5, basically. So you divide n2 by the square root of 5. It is 2 the square root of 5, 1 square root of 5. This is something like a convention, and you can use this convention basically to agree on an eigenvector, on a specific eigenvector. All right. So this is the eigenvectors and the eigenvalues. And this is the last thing I wanted to discuss today.